All right, we got a few people on the call already. Thank you everyone for joining us today. We will be getting started in just a few moments. We're gonna let people grab their lunch, find their Zoom links and join in. So stay tuned. We'll start very shortly. We got a couple more people joining the call. I just want to let you guys know we will be starting very shortly. We're just gonna wait a couple more minutes and let a few more people join the stream. All right. Well, I think this is probably a good time to get started. Thank you, everyone. Good morning, everyone, and thank you for joining us today on such a lovely Wednesday. Today we have the amazing Reed Spencer with us. Reed is a VP of technology here at Improving. Reed has over 25 years of experience in the industry, specifically around architecture and specializing in reactive architectures with Akka in the last 10 years. In his free time, Reed loves music and he loves scuba diving. And he says he is a spoiled 80 AV tropical diver, 80 feet visibility, 80 degrees Fahrenheit water temperature. Now, this presentation is about scuba diving, but without any further delay, Reed, please take it away. Oh, sorry, real quick before I hand it off, sorry. If anyone has any questions at any point, please feel free to post them in the Q&A chat at the bottom of your screen, or send us a quick message and Reed will be happy to answer them. And sorry about that, Reed. Here you go.
No worries. Thank you for the warm welcome, Jordan. And we're going to be talking about developing modern applications with design patterns. There's lots of design patterns. We're going to just talk about 4 of them today. Assuming I can get to the next slide. There we go. So last week, Michael Perry took us through the use of application models to drive success. And the link to that talk is on the slide there. Once an application's requirements are understood through creating a model, it's time to consider the design and to do so in more detail. This presentation will explore 4 design patterns, as shown on the screen there. These are the 4 we selected to present because they are likely the most important patterns for modernizing a software system. There's many more. Follow me on the blog here and I'll get into the other ones as well. So the first pattern up is the Strangler Fig pattern. This is a metaphor that was created by Martin Fowler back in 2004 or thereabouts. And it came about as he took a trip with his wife to Australia. And they spent some time in the rainforest in the Queensland coast there. One of the natural wonders of the area is the huge strangler fig trees, which are shown on the slide here, just to give you an idea of the kind of complex patterns that they generate. These trees seed in the canopy. So they start out at the top of the tree and they work their way down to the root into the soil so they can root down there. Over many years, they grow into fantastic and beautiful shapes like the one shown. And meanwhile, however, they are strangling and killing the host tree that they grew up on top of. And it turns out that this is a pretty good analogy, an excellent metaphor for incrementally replacing an aging system. So that's what we're going to talk about first. Let's go into a pattern definition of this. And this comes from Azure website. That's the Strangler Fig pattern. And I'm just going to read it because it's really quite clear. Incrementally migrate a legacy system by gradually replacing specific pieces of functionality with new applications and services. As features from the legacy system are replaced, the new system eventually replaces the old system's features, strangling the old system and allowing you to decommission it. So the thing to note about this is the highlighted words. This is the opposite of a big bang approach. We are not going to build another system completely separately to replace the older system and then just cut over one day. It's intended to proceed gradually in well-defined increments, so the old system is eventually replaced to the point that it can be decommissioned. At one client, this process took 5 years before all the functionality was migrated away to a new set of microservices. So this is not the fast way to solution, but it is the careful, safe way. So we're going to get into this in a bit more detail. So the strategy for applying the Strangler Fig pattern is pretty simple. You start with your legacy system, and we're showing that as a red dot up there at the top, right? And you then want to analyze and decompose that system into components that have their own APIs, shown here with the 4 arrows. So just think of each colored arrow as a separate component that has its own API. And that initial application is, completely implemented in terms of the legacy system. So this isn't really adding anything new except for some infrastructure. And then finally, you want to fully develop each of those things incrementally so that you eventually replace the legacy system and it's no longer in the picture. So that's it in a nutshell, but we recommend a process to accomplish this. And first, there's a bunch of questions that you want to ask of yourself, of your team, of the experts of the legacy system. Questions like this: is the application amenable to replacement by iteratively replacing its components? In other words, that process I just showed you, is it even viable to do that? Because if it's not, then this approach isn't going to work. You have to try a different one. Does the legacy system already have an API you can use? Is there something that you can just easily pick apart and compartmentalize and do replacement gradually? If so, can it be used to derive the needed components? Can we use DDD to derive subdomains, bounded contexts, aggregate entities from the legacy system? If not, can it be broken down into logical components some other way? There's probably many other questions that need to be added here. These are some of the just sort of obvious ones. But the thing is to analyze this thing carefully, because you don't want to break what the legacy system does, which means you need to understand what it does and build your API up from that functionality. So second, you want to design those components that you identified by answering the first question. So the first thing is review the answers from the previous step. Then ensure you've covered all legacy system functionality, right? So make sure that you've got each component covers something, and that everything that the application does or the legacy system does is covered by the API that you're designing. And then, use domain-driven design to factor out bounded contexts and entities. Those are typically the components that you want. If you're not familiar with DDD, bounded context is a very well-defined set of messages that would go into a particular system. So you're defining an API through a bounded context, and then entities are the things that bounded contexts are made out of, or there might just be one entity for a given bounded context. But the idea is to divide the complexity of this thing into discrete pieces that you can define. And then it's just defining the message APIs for those entities or bounded contexts, and then sort of take a step back and look at the interactions between those things. If they're too busy, you kind of want to minimize that. You might want to slightly tweak the entity boundaries or whatnot and try to keep it low volume. We'll talk more about that later in a different section. So finally, the third thing, if I can get my slide to go, is to deploy the components. And this is actually sort of develop and deploy. So you want to do the entire development process all the way through to deploying a component. So, work incrementally one component at a time, but order the component deployments to get the most important payoffs first. There may be some sort of ancillary parts to the legacy system that aren't used that often. You probably don't want to start there unless you're nervous and you want to try take a low impact thing. But arrange the deployment of this thing in so that it pays you back to the greatest amount. Whether you're cautious or aggressive, just whatever your priorities are for deployment, make sure that's understood early. And start each increment with a pass-through. So just like those 4 arrows pointing in, that's the pass-through. We've defined the API. We've changed all the uses of the legacy, or one component at a time, so that they're using that pass-through implementation. And then the implementation is just passed through the legacy system. So theoretically, you don't have any functional changes at that point. But it's important to get all the users of the legacy system using this new API. Then you want to fill it out. So deploy that API with the pass-through implementations first, then prove each increment functionally. So separately test, like each of these pie wedges here as you're going through it. So you're working on a component. So you're working on the blue component here. You want to make sure that completely works, and then deploy it. And maybe let it sit for a day or two and see if there's any issues arise, fix those before moving on to the other components. So as you do that and you go around these pie wedges, you're slowly moving functionality out of the legacy system. And when you get done, you can probably turn the legacy system off. So why do you want to use this? So the main reason is right there on the screen. So reduce complexity by isolating components first. So that's just a simple divide and conquer approach, right? Just let's only look at part of the problem one at a time. And you can do that if you've kept the boundaries between those things really clean. You're using bounded context, so there's very little interaction between those components. Reduce risk to incremental delivery of small changes when compared to a cutover delivery. So this is the alternative to just writing a whole new system and cutting over to it. And the ability to phase in the important components earlier than with the big bang cutover. So if there's going to be any surprises, it's better to know about that sooner than later. So that's the Strangler Fig. Oh, one other thing you should consider. This new system that you're creating, it's using the Strangler Fig pattern, is eventually going to need to be replaced itself. It may be 10 or 20 or 30 years later, but there'll be something new that comes along and replaces that. So design that thing in such a way that using the Strangler Fig pattern in the future is easy. In other words, just make really clear API boundaries and very clear conceptually what those components are, so that somebody else can slice and dice it with new technology later on, and document that design. Oftentimes the internal workings of legacy systems are not well understood, and so you should make them well understood in this replacement. Okay, moving on. So the next thing we're going to talk about is microservices, but not just any kind of microservice, autonomous isolated microservices. Again, this is how we tame complexity.
Hey, we had a question come in about Strangler Fig pattern.
Yeah, I see it. Are there recommended ways for the team to track their progress towards done? Recommended, no, but I mean, if you use Jira or some other kind of agile project management tool, there's lots of them. Every one of those components and all of the pieces to build them should be tracked in there as tickets. And that's sort of the only recommendation I can make here. You do need to track it. So fair amount of analysis at the beginning. This is not the quick, easy, fast way to do it. It's the careful, slow, cautious, and safe way to do it. Hopefully that answers your questions. All right, I'm going to assume that since there are no open questions, that we can move on. Autonomous isolated microservices. So we contain complexity. And we do this, I've got a lot of words on this slide for a reason, because I actually want to go into this in quite a bit of detail and want you to read and understand these words. So I'm going to just read this. So autonomous, what does autonomous mean? A system component that is single purpose, does one thing, self-supporting, right? So anything, it can get its own resources, is independently deployable and automatically releasable. So that's what we mean by autonomous. And we'll go into all these words in detail in future slides. It's also isolated. And by that, we mean isolated in 4 dimensions. So space, time, state, and failure. We'll go into each of those things, but it's isolated from its peers and any of the other microservices. Those are key factors in making a very well-designed set of microservices. And then what do we mean by microservice? There's lots of different definitions here. So what we mean is a small, decentralized, clusterable message passing process based on a bounded context, that's from DDD, that is a component of a larger distributed system that communicates over a network to fulfill some specific business capability. That's a mouthful, but we're going to go into all of these things and in the coming slides here. Okay, so autonomous. The first thing is single purpose. It does or represents one thing completely and well. So that's what we mean by single purpose. It might be representing a process, or it could be representing an entity. So a thing or a process. And it should do so completely and well. There should be no need to go anywhere else for that particular functionality or to gain information about that particular entity. Okay, so single purpose. Self-supporting. So the next thing here is that it's really the autonomous part, right? It's doesn't require its dependencies to be functioning well. In other words, if it depends on other microservices, they don't even have to be running. It may need to cache something initially or lazily. So it may need to fetch things from other things, but it only has to do that once. Manages its cache, maybe it times out after a certain amount of time, but it does whatever is appropriate in that business context for it to function, regardless of its peers. In particular, it should strive to prevent cascading failures. So the situation where you have one microservice failing and that causes a failure in another one, causes a failure in another one, that's a cascading failure scenario. And we want to prevent that as much as we can. So they're independent, autonomous, self-supporting. The other thing is, the next thing is independently deployable. So they're packaged with a package manager of some sort. And we package them for easy automated deployment, maybe a container image. It might be, the Debian package. I mean, it just depends on the nature of the beast of what you're trying to deploy and to where. But it should be packaged so that it can be independently deployed. And that's not independently deployed. Doesn't just rely on packaging. You've got to maintain a backwards compatible API. In other words, you should be able to pull that service, microservice, out of service and replace it with a new version. And the other peers are unaffected, right? So the API has to be backwards compatible, at least to the oldest version that's still running in production. Once older API things are not in use anymore, then you can pull them out of the code. But maintaining that backwards compatible API is very, very important, and it's often a step that's skipped or just not thought of by the engineers, and it causes problems. So it's something you need to pay attention to. No, the other thing is it knows how to find its dependencies. So if it needs to query something else to get to get some data, then it should do that early or lazily, and it shouldn't fail when one of those things is not available. It may have to delay a request if it doesn't have the data, or if the data is too old and it needs to refresh its cache, etc. It's got to play all those kind of cache dependency issues, but it should never fail because one of its peers are not available. And it needs to ascribe to the fail fast philosophy, which is you can bounce it easily. In other words, doing a kill -9 on that process is just fine. It should be completely resilient to that. So if you can get to those kind of things, then you'll have these independently deployable things. They can be restarted anytime, even sort of brutally hard with a forced shutdown like kill -9. Or you know, and when it comes back up, it just integrates into the mesh of services easily. So that's what we mean by independently deployed. So the next one is automatically releasable. So this involves, you know, actually getting it into production and releasing from hopefully a CI/CD pipeline. So two different versions can concurrently coexist. Remember that they are backwards compatible in the API, so you can actually do a rolling upgrade strategy where you don't take anything down out of service, you put in a new version while the old version is still running. And once that sort of picks up some of the load, then you can roll the other one out. If you've only got one instance, then of course you have to wait for all of the load to roll over to the new version. Configuration should be external. In other words, you control the configuration outside of the image or the package. Quality checks should be performed automatically. In other words, before you actually get to releasing that thing, you should have gone through some quality gates. You know, run the unit tests, run some of the integration tests, etc. Make sure that it's working before you actually try to roll it out. And then finally, just, you know, using that rolling upgrade strategy. Okay, so that's it for autonomous. So the next thing is isolated. And I remember I said there's 4 dimensions of this. So when we're talking about this, you know, we want to isolate our microservices in the 4 dimensions. The first one is space. So space is, think of space as location transparency. In other words, where in the network space is it running? And what do you need to know about its peers? So you want to have this notion of location transparency. It's like the application itself doesn't know and doesn't care where it's running. We assume that all communications to peers or to other copies of itself are remote. So we build it for remote, which means that they can fail. So again, let it fail kind of approach to implementing it. So what this really means is it operates regardless of the physical location. And by physical, I mean the network location. So is it in the same Kubernetes cluster? Is it in the same pod? Is it in a neighboring Kubernetes cluster? Is it in a different data center? Is it across the world? You know, those different locations shouldn't matter. So you need to design it so that you are isolated in space. So there's no difference between a local and remote call, except that you've designed it for remote calls. The next one is time. So we want to use an approach in the implementation of this surface where we're isolated in time. What that means is essentially using asynchronous non-blocking communications. So you can, if you design your system to asynchronously interact internally and externally, that maximizes your resource utilization. In other words, you're not going to allow any thread that's running in your application to block ever. Now, that's a little extreme statement, but you really want to minimize the blocking and to use non-blocking communications best you can. So essentially, because the threads aren't blocking, they're able to run, you know, that CPU full time. The worst thing you can do is block a thread, which has a huge memory implication in the operating system kernel. And if you have lots and lots of threads, then what happens is your operating system is just going through scheduling. Mostly he's doing more scheduling than actual work. So you want to keep the number of threads in use down. Ideally, it's to the same number of CPUs that you have so that every thread is just constantly running on a CPU. That maximizes your CPU utilization. So We never want to make a CPU wait for I/O, for a lock, or anything else that can block a thread. So that's the goal. Doesn't always work out perfectly with that. Sometimes you have to wait for I/O. But if you can put that I/O wait on the side in a different thread, then you can keep that core set of threads doing actual application work. So this is an efficiency thing that we want to bring to an isolated microservice. Another area of isolation is about state, about the data that it stores. So most applications have to store data persistently somewhere. It doesn't have to be a database, but it could be in VRAM or shared memory or anything like that. But we don't want to actually share that outside the microservice, even if it's shared memory. So that microservice should have free control over the schema or the database type than anything being used by any other microservice. The more degrees of freedom you can give there, the better off that microservice will be, because it has total ownership of its state. And this stuff happens, like, you realize that, oh, hey, this relational schema-based thing that we started off with isn't scalable enough for the current usage, so we need to change it to a NoSQL database that's distributed, say Cassandra or something like that. You should be able to do that completely within the implementation of that microservice, and none of the other microservices are affected. That's not sharing state. So we're isolated in state. We don't allow anybody to dip into our database. If they want data from our database, they've got to come through our API. So no sharing data except by API. And the last one here is failure. We want to be isolated in failure. Notice, if we fail, it shouldn't propagate everywhere else. So it operates even when its peer dependencies are not functioning, and it usually implies caching of needed data. If not, you may go into a slightly adjusted operational mode where data is not available right now, but that's an expected state of operation, and it doesn't cause your microservice to fail. Data outages happen, networks go down, things happen, but your service needs to be able to survive that. So isolated and failure means we don't cause other people to fail. We just keep working as best we can. Okay, so that's isolation. Next up, we have the complicated definition of microservice that I showed to you earlier. So if you recall, the definition was small, decentralized, clusterable, message passing process based on a bounded context that is a component of a larger distributed system that communicates over a network to fulfill some business capability. We're going to go through that clause by clause. So small, it doesn't have anything to do with the number of lines of code, right? That's not what we mean here. This goes back to that single purpose thing that we talked about earlier. It must deal with only one abstraction, one entity, one process, and this is to limit to bound the complexity of that abstraction. So it's single purpose, as discussed under the autonomy slide. Is message passing. So if you've noticed, we sort of have a penchant for using DDD for design here. So the idea is to use, to derive a bounded context for this microservice and define your API around messages. So DDD is all around messages. We also think it's the better way to build a system because you can segregate things. There's things you can do with message passing that you cannot do with RPC or functional calls, and especially things like caching the calls. It's very, very difficult to do that with RPC. So you can put it into Kafka. You've got many more options for building a large, complicated system if you can cache the messages. So define your API around messages. If you think about it, it's equivalent, right? A function call can be turned into a message. The message contains the parameters, and the response is another message. So we want to define our microservices around 4 kinds of messages, and this comes right out of domain-driven design. So there's a command, which is a request to perform a state change. There's a query, which is a request to provide some information without a state change. And an event, which is the result of processing a command successfully. In other words, recording the fact of the state change. And a result, which is the result of a query that provides the requested information. So we can break all APIs down into just those 4 types of messages. That we'll get into that a little bit more when we start talking about CQRS. What am I doing on time? Wow, really? I've talked for 45 minutes already? No.
I'm seeing 12:30.
I'm halfway through. Okay, thank you. Looking at the wrong clock. So the next thing is distributed. Okay, so that's kind of what the picture is showing here. We've got an API gateway that the client's talking to, but it distributes the requests across the microservices. Whether those are different microservices or the same kind of microservice, you can do this for load balancing or just for functional abstraction. So, it's got to communicate efficiently over network using a good protocol, treats all external communications as potential failures. So when microservices are talking to each other or to the gateway, those are all potentially failable communications. You need to make sure that you've done the error checking and that it doesn't cause your application to blow up, or your microservice to blow up. We also want it to be clusterable. In other words, we want to cluster these things for scale. So this is what I mentioned about handling larger load. It must be possible to create additional instances of the microservice and have it work cooperatively with its peers. This allows horizontal scaling by utilizing additional computing infrastructure. And then finally, it needs to be business oriented. In other words, it fulfills some business objective. It's not just there solely for technical reasons. It actually is part of the business solution that you're working towards. And it has relevance to conducting the business or supporting customers. Okay, so that's what we mean by microservices. Some precautionary tales here. So we don't want your network of microservices to ever look like this picture. So don't let it become this. There can be a tendency to think that boiling everything down to microservices is the right way to go. That is typically overkill. However, without some forethought as to the design of the overall system, you can get yourself into a quagmire of complexity quickly, and that's what we're showing here. So here's some tips. Microservice boundaries need to be informed by your DDD design. More is not better, less is better. If you truly have several hundred kinds of entities, there's probably a way using DDD to create an aggregate entity. And typically aggregate entities are the things that receive messages. And therefore you can aggregate several entities together, and you don't need a microservice for each one. If you've got 1,000 distinct concepts that cannot be clumped together, okay, then it's appropriate to use 1,000 microservices, but that's super atypical in most business domains. Again, single purpose comes up. Each microservice should have a single purpose and fulfill that purpose only and completely. So you don't want to have some of its functions over in this microservice and some of its function over there. No, that's one thing. You also want to design your system so there's low coupling between microservices. Low coupling means there's few interactions between the microservices as possible. Network communications overheads can add up, so we want them to be meaningful and infrequent. In other words, feel free to batch things in a single request. Use small messages. Factor communication latency into the design. Good rule of thumb is to do 1,000 times more computing than the communication overhead. Say the communication overhead is 10 milliseconds. Well, you should do 1,000 times more than that, a few seconds worth of computing. It's a rule of thumb. It's not, don't get dogmatic about that, but you should think about it as, yeah, we're going to do significantly more computing than network communication. Why? Because if you don't do that, the amount of network communication is going to be the bulk of what your application does. So think about that as you're designing your microservices. Similarly, high cohesion is something you can use to find your boundaries for your microservices. Your system design should exhibit high cohesion within a microservice. That is, don't distribute a small computation. If there's an algorithm implemented in a variety of functions, put them together in the same microservice. A whole bunch of calls to functions, don't distribute those across the network. You'll just slow everything down. So where there's cohesive function calls, keep them together. Even if the same function occurs in other microservices, right? It's okay to reuse code in a library, but a copy of that library needs to be in each microservice, right? You shouldn't make a remote call just to run a single copy of some function, right? It's okay to distribute those functions and to reuse them in different microservices. So again, we want those microservices to be isolated so that those invocations stay local and fast correspondingly. It's okay to reuse, but each microservice should have its own copy and not rely on remote invocation for something small or fast to compute. And finally, event-driven. So enforce the use of clean APIs only. Don't integrate by directly sharing any kind of storage. Again, this goes back to the state isolation, right? We don't want to share storage between microservices. For processing that takes significant time, use a message queue. Answer API requests from memory caches so they are always the fastest. Don't fracture a bounded context into multiple microservices for CQRS by default. You can do that, but the only time you want to do that is splitting it apart if one component needs to scale more than another. We'll get into CQRS and some of those discussions in a little bit. Most importantly, do not give them short, cryptic, uppercase, mnemonic names as shown. That's not a hard and fast rule, but it sure helps if people can look at the name of something and sort of grok what that it's about right away. All right, as promised, we're going to talk about CQRS. So what is this? It's command, query, responsibility, segregation. It's a pattern that's come up for the last 15 years or so. And we're going to talk about it with event sourcing. In fact, we're going to talk about event sourcing first. So the basic idea is in that picture in front of you. So you've got some UI or some external client, and you're going to come into a service that has two sides. It has a command side and a query side. So there's a query model, we call them a query model or a read model, and a command model or a write model. And that's the segregation. The responsibility to read and to write is segregated into different components in your design. That's the pattern. Now we're going to get into the details of that. So first, what is event sourcing? Because it's important to understand event sourcing first. So it's a way of storing state as a ledger of facts. So what we have here is like a row out of a database, and that is not a ledger of facts. That is just a row. It's the net sum of a bunch of facts. So what does a ledger of facts look like? It looks like this. So the order 23 was created. Okay, we see that in the ID column. An item is added. So an apple, pork loin, sauce were added. So that shows up as items is 3, but the table doesn't show us which items are there. Then we computed some tax, and that's shown in the column. And we have the total computation, and also the order got closed. So the final status is there, but we don't show that it was ever opened. So there's a little bit of loss of information going to that table. And in fact, it's true that you cannot go from that table to the events that would create it. All right, there's a loss of information from those events. So I have to figure out where I was in my notes. So the log of events is the system of record, and you can always go from that system of record to the table. That transformation is always doable. So we can always lose some information to store a summary. We can't go from a summary back to the origin of what happened in the system to create that. Tabular representations of the current value can always be reconstructed, replaying the events through a projector that yields the tabular representation. The projector could just write into a relational database, for example. Additional representations, time series, graphical, hierarchical, can be constructed to satisfy different views. So it's not like you have to go to a relational table. You could actually construct a graph of those events that occurred, those facts. Or you could do a time series thing, see how it changed over time. So there's lots of ways to present that in summary or high level form, but the system of record is that list of events. So because it's the system of record, it means it's the primary source. All other replications of that data are projections from the event source. So the well-designed events can provide much more detailed information, as you saw in that list, right? In the list of events that happened, you got 3 item added. And so we know that in this particular order, there's apple, pork loins, and sauce. But the tabular form doesn't show any of that information. So it's information that gets lost. So the event log is usually much richer in information and detail. Excuse me. Apparently need to wet the gullet there. Okay. It turns out this log event is quite suitable for things like fine tuning on AI model. Event logs can be used for data analytics too. So we'll look at that. We'll look at that on the next slide. First, we're going to do some benefits of event sourcing. So the first thing is write scalability. Because you're writing a log, event sourcing uses the fastest kind of update in any medium. It's appending to the end, right? We don't need to seek the head. We don't have to do any kind of lookup. There's no indexes to update. It's the fastest thing. We're just writing a blob of data to the end of some file, database table, whatever. No indices need to be updated. That's a read side thing. Solves the relational database problem of trying to balance the schema for fast read and write. If you've ever done any relational database administration, that's always a tug of war. How do we make this thing do super fast reads and queries, solve queries very quickly? Usually means a lot of indexes and whatnot. That tends to affect the right side. It makes the right side slower. So by segregating these things, we get the especially relational database out of that situation, right? So we have write scalability. We can do the fastest kind of operation available on any medium. Debugging. So it provides a record of the flow of events, right? So you've got this log of what's going on. It makes debugging easier because you can see exactly what happened at the point that you're investigating. Current state of read side projection can be repaired by replaying events with the fixed code. So in other words, if you have a bug in your code and you fix the code, you can fix the projections by just playing the events back through, and it will naturally fix itself. Customer support is enhanced. Again, you've got more detail and it's authoritative history of all the changes to all the entities. And if you use that in your customer support model, then you've got a much richer set of details that can be used. It also helps with non-repudiation. So then there's resilience. State can be restored after a crash up to the most recent event that occurred. So if something crashes, we can replay those events again and get right back to where we were. It may be an incomplete set of operations, but that's where you were and that's where you can get back to after a crash. Snapshots can be used to minimize disk space accumulation and speed up data restoration. So this is the idea of, okay, we'll take the current state and put that as a marker in time. Everything's a change from that marker of that snapshot. State is typically saved in a more fine-grained manner than saving only the end result of a transaction, which turns out to be a resilience feature as well. Audits are enabled. So, if you have to go through an audit, now you've got all the details of everything that ever happened. So audits are supported because every action taken results in a state change in the model that was recorded with an event. And transformation, you can that log of events, as I was showing on the other diagram, can be transformed into any kind of thing, right? Any kind of database structure: relational, flat, hierarchical, graphical, real time. You can always create projections to allow the read side to proceed more effectively, or for the kind of view that is wanted. Okay, so those are the benefits of event sourcing. Now we're going to talk about just some of the applications, and I'm going to speed through this because I'm a little short on time. So you can use it for data analytics. So the event source becomes an event stream. So as you're saving your events into that storage medium, you can also create a stream out of it. So you could use Kafka or any other streaming system, Akka streams, and that becomes an event stream. It turns out the event stream, can be used for data analytics. It's exactly what they want. You may need to do some computations and apply them to things. You might do some aggregation or some filtering or some actual computations like summation or averages, etc. If you're using a qualified stream system, you've got back pressure and data loss are just automatically handled. So the system will sort of respond to the pull for information to the flow. And you may need to put aggregators in there if you've got a big mismatch, like if the end of that data pipeline is a display like we're showing here on this slide. You may only want to update that every few seconds, every 5 seconds. But if those messages are coming in at 10,000 per second, you've got to do some aggregation to filter it down to something that can be displayed at the right rate. It's a natural fit for real-time data analytics. And here's an example of a broadcast. This is from Colin Brooks' blogs on this topic. And this is a broadcast element. If you look at the numbers, you can see that each of the messages are coming in on the left side and they get broadcast out. So you get the same messages going out at the same time in four to four destinations. So this helps keep things synchronized. There's lots of patterns like that. The opposite, a merge, multiplex, aggregate, summarize, split. There's tons of them. So that's all good. And that's all because you based it on event sourcing. So this is the utility of it here. Another utility for it is AI ML training. So, the quality of an ML model is really directly related to the quality of the data it was trained on, because every event in an event source is a fact. It's something that actually happened. There's no ambiguity about it. It's definitely something that happened. So here's a diagram that shows the usual process where you get the data. Obviously, the event source is the stream of facts to be used. Events form the system of record, therefore they should be clean. You don't have to do a whole lot of additional cleaning and manipulation. So ensure they don't need any cleaning by putting things like timestamps into them, because if they need to know when something happened, that's important. Train the model, obviously, use the data to train the model on all the events you have, both historical and concurrently. Factual outcomes from ML are often events. So when you use high quality data, what the ML tells you is additionally new data that can be used to validate the training of your model. So that's for the testing the data. And feed every new event occurring in your system directly into retraining your ML model. So you can do this all in real time to improve that model also in real time. Okay, so those are some of the uses. We're going to get into CQRS now. So this is the command query responsibility segregation part. That diagram is what we're going to be walking through. So first, the blue right side, on the right side of the diagram, it takes in commands, it produces events. The events get stored to an event store. They also get sent to a projector. The projector updates the projection store so that when a query comes in, going up the top right now, it comes into the read side, which needs to produce a result. But in doing that, it can query the project store, or it can read the memory cache. So I've got those purple things are like the memory cache of an aggregate root entity containing another entity. Those things can be loaded out of the event store. And that's sort of a model of how this works. And I just went through sort of the read side, and the projectors are just code that takes events and turns them into some other update in some other database. Right? You can think relational, but it might be in NoSQL. And then the memory cache part is those, the in-memory copy of things that you're updating, doing that for faster responses. There's some pros here. Separating write activity from read activities allows you to use the best storage technology for the task, right? So your event store might just be a flat file and just append to it. That's pretty fast. It may be a relational database that you've got a table where you just keep adding rows, or some other specialized thing. The point being is that it is not the read side storage. So the projection store or the read side store can be whatever relational database or NoSQL database is best for satisfying the kinds of queries that you get. So if people want to know about, how does this change over time and need a big, long response, then you might want to use a time series database. So again, they're separate, so you can pick the best technology. It's very common to place the command side storage in an append-only log, even a file will do. Read activity tends to be more frequent than writing, so you can reduce response latency by placing read data sources in strategic geolocations for better performance. In other words, if you need that data to be close to the end user and you've got a global user community, you can put that in copies of those projections. So the projection just doesn't only have to happen to one database. It could happen to a whole bunch of databases all over the world. Separating write from read activity leads to more efficient scaling of storage capacity based on the real world usage. Allows most scalable storage solution to be picked for reads and writes. And updating the read side has no write contention. Right? So that projector is happening after the event store, right? So this event to event store thing here, that happens first, and then you send the event over the projector. They can't contend for write, right? There's only a single writer here. This write side is writing this event to the event store. Nobody else is writing it. So you don't get contention there. Okay, so there's a few cons as well. You may need some expertise in different kinds of database technologies, not just one. So instead of just sticking with a given kind of database, you might have 2 or 3 different kinds to satisfy the queries best. So that's one complication. CQRS ES usually requires more storage space because you've got the event store, which is the system of record, and then you've got your projection stores, and there could be a whole lot of copies. It's not unusual to see, some entities that have 2 or 3 or 4 different projections to satisfy different kinds of queries. So that can be considered a downside. It's also an upside in that you can get the best performance for each of those queries. You can utilize mobile kinds of databases, which can increase the cost. So there's a cost implication here. And it usually requires the acceptance of eventual consistency. So there's a little tiny lag that happens. So when you do a write side, this event is appended to the event store. And then the projector, and this isn't really shown here, the projector is going to update the projection store, but actually it is shown. I'm sorry, this path here where it says updates, the event updates the aggregate root entity, which may go down to some other entity. But this is a memory copy. So there's a slight little delay from the time that it gets into the event store to the time that this gets applied as it changed here. We're talking probably microseconds here, but there is a little bit of eventual consistency that happens because of CQRS. And your system has to be able to deal with that. Usually the lag is very small, and most, eventual consistency is the way the real world works anyway, so it's not really that big of a deal. All right, that was a whirlwind trip through that. I'm trying to get through the content here in 6 minutes. So this is the last section. So we're on to a new pattern now. This one's called workload partitioning. And that is a diagram of a partitioned set of data that can be use to get some benefit, get some performance out of out of solving your workload scale issues. So this is about conquering scale and doing it elastically. The question comes up, wait a minute, partitions at what level? Aren't those just for databases? No. You can actually use partitioning at the application level just as easily. So it's a divide and conquer technique that databases use to distribute load across a bunch of slow storage devices. And we can get multiple writes going. Dividing workload across multiple disks means more writes can be done concurrently, hence your scalability goes up. So you can do this at the application level too, right? As the input is coming into the application, we can say, okay, who's this for? And partition it up into different processors to handle the requests. So it's an excellent way to handle application load because it applies the divide and conquer technique at the application level. Here's how it works. Here's how it works. You have a cluster of nodes. Now, so look at the diagram as I'm talking about this. You have a cluster of nodes ready to take requests. Each node hosts a shard region. Okay, those are the orange circles. A shard is the same thing as a partition. So one of the nodes is the shard coordinator, and that's the purple one. The shard coordinator deals with nodes or shards, or the shards that a node represents when it's entering or leaving the cluster. Okay, if the shard coordinator fails, the next oldest node becomes a coordinator, probably the yellow node, number 2 there. That's this one here. It's hard to tell the difference between orange and yellow here, but number 2 there would be the backup coordinator. Each shard region hosts a number of shards. Those are the green dots, right? So every one of these greens is a shard. So this one here, number 4. Sorry, I should be pointing at the screen here. This one here, number 4, has 2 shards, this green one and this green one. And then these are all the instances in the shards. And those are the blue ones. Shard region 5 in orange is showing routing requests to instances in many shards and shard regions. So this one here has all these lines coming out. The other ones don't. They just have the containment of the shards lines, but that's done here just for illustrative purposes. And it can route from here directly to these guys, just following these lines here, and etc. to a whole bunch of places. This one over here too. Okay, so that's part of what they have to do is routing requests. Consequently, any shard can route to any instance. Furthermore, every shard region or node can participate in routing. Only one set of such routes is shown to make the diagram comprehensible. Routing uses a unique key extracted from each request that you use to compute the partition on which that entity resides. Okay, I'm just gonna bolt forward here so I can get done in time. So there's a number of partitions we have. What's the right number to pick? So we want to figure this out using scalability laws. Linear scalability is not the way to do it. It's a fantasy. Real systems don't work this way. Linear scale can be achieved as long as you don't use memory or storage. And the parallel algorithm is a computation that needs no coordination between the partitions. You might be able to get close to linear scalability, but useful parallel systems aren't like that. So that's not going to work. Amdahl came up with the law. There's always a serial part in any computation in Amdahl's law that limits the return of the parallel computations. This means Amdahl's law defines the theoretical maximum for speed up. And you can see that here in the green curve. It's like, okay, you know, we can't get linear scalability, but there is some maximum based on how long our serial part takes to compute. Gunther went beyond Amdahl's law with his universal scalability law, and he showed that, well, actually it's worse than that. There's diminishing returns compared to Amdahl's law. So things like coherence delays and contention, these things factor into actually reducing the amount of scale up you can get. So let's look at some of the consequences here. Linear scaling is a fantasy. There's always a point of optimal parallelism. If you look here on Gunther's law at line 8, that's the best point. You want to have 8 processors because that's going to give you the most scale. any additional processor actually could reduce the amount of throughput that you get. Okay, we should minimize several things: the serial part of the parallel computation, contention for shared resources, and the cost of achieving coherency between partitions. I am so 1 minute left. Okay, some consequences: be aware of these laws and minimize their impedances. We want to go through choosing a partition key. I want to blast through this. It's actually quite simple. So uniqueness, a key has to be unique. It has to have a flat distribution so that it's just as easy to compute for one partition as another. And then you need to have, it needs to be something that you can have a hash function for. So it's a piece of data that you can develop a hash function for. By the way, these keys are terrible. Using alphanumerics for keys does not have a flat distribution. You're going to get way more E's and A's and other vowels than any other letter. So don't do that. Then you need a random or a prime number, and you can compute it by generating the hash function, dividing by the prime. That gives you which partition the entity is in. And then the big thing here is that we want to minimize the serial part. The serial part comes from Amdahl's law. So request routing is the serial part. So when you're trying to go from number 5 to one of those other ones, you need to figure out which partition it's in and send the message forward. For best performance, we want to minimize that part. So here's the formula for the speed up that you can get. The serial part is this 1 minus p part. It's 100% of the time minus the parallel part, and then you add to that the parallel part, and it's 1 divided by that. So it turns out that if you look at different values of p here, so in other words, if the serial part is half the workload, you don't get much scale up, right? After 5, you got 5 times the resources, and you're only getting 1.66 times the performance. At the partition part being, the parallel part being 90%, 10% serial part, then you've got up to 3.6. And of course, if you can get all the way to there is no serial part, then you're at linear scalability, and then it scales linearly. So the main point here is just use Akka. It does all this for you. And this diagram actually comes from a video on Akka. So I'm done. Thank you. Sorry that was rushed at the end. I will try and trim that up a bit more next time I present this. Next week, Terrence is going to give us building incremental assurances, alleviating uncertainty through incremental change. That will also be an excellent talk. I'm looking forward to it. And that's it. Thank you.
Well, thank you so much, Reed. That was an amazing talk. And I know it's a ton of content to fit into just 1 hour. So somehow you figured out how to do that.
Apparently. Not as well as I hoped, but
well, thank you everyone so much for joining us today. I really appreciate it. It's great to have you on here. And it's great to have you as a speaker. Reed, you're welcome back anytime. As Reed was saying, please join us next week, same time and place. Just gotta register for that next event. We have Terrence Prasad, who is here with me in Houston, and I know him actually very well, so I'm very excited for his talk, and I'm looking forward to it. Definitely would recommend not missing that one. And we hope to see you all back. Anyway, have a great rest of your day, and see you next time.
Thank you, Jordan. And if you need to reach out, grab my email there. I'm happy to talk about these things with anybody. Thank you.
Absolutely. All right.